Hello there, Mr. Sutton here with the BC Calculus 8-6 Extra Practice number 1 solutions on advanced polar area. On this calculator-based free response, we've got the figure here for r equals all this craziness, and we have this other one here as well. Now, I'm going to officially define r of theta as this thing up here. I mean, they said r equals, but r is kind of generic, like a y equals or an x equals. So now I've really defined all this stuff as r of theta, so I never need to write it again. Okay, so we want to figure out the area of this region bounded by r and the lines theta equals 0, so that's just the ray going out to 0 radians, and also theta equals pi over 2. So our general area formula, we've got 1/2 times r squared d theta from a to b. In particular, on this one, we're going to have an integral from 0 to pi over 2, from here to here in terms of angles, of, well, just this r function here, which I can now write as r of theta, well, this will be 1/2 r of theta squared d theta. And I just plug this in the calculator. So here I am on my calculator. And you always have to decide when you're doing these problems, do I want to enter these in the polar mode or the function mode? And just kind of looking ahead on this problem, I noticed there are things I need to do with r that involve solving for certain values of r, and I can't do that in polar mode. All polar mode's really good for is graphing. So I went to y equals mode, and I'll graph it in polar mode if I really need to. But here's what I've got. I've got y1, that's this r function here. And for y2, I actually entered in their derivative that they just kind of spelled out for me. I mean, I could have gotten this on my own, but thank you. So we'll probably be using that later as well. So I need now this stuff on my calculator. Let me quit out of y equals. So we have math 9, integral from 0 to pi over 2. So here's pi over 2. And inside here, I've got fancy fraction 1/2. So that's 1/2, and that's going to be, we now have this as just r squared, so that's going to be alpha trace y1 is where I stored my r function, and let me square that. So much easier when it's stored as a function. Put a little x there for dx, which is really the same as this d theta. Press enter, and that comes out to about 6.194. For this part of the problem, they want us to find the area of the region in the first quadrant, so in this graph here, that's outside the graph that they just gave us, which we're calling r of theta, but inside the graph of the circle of radius 2 centered at the origin. You could graph this on the grapher in polar mode, but it's a circle of 2 with a radius of 2, so I'm pretty sure you can draw a circle like from here to here, and it would go all the way around, but we're not showing everything. So there's our circle with radius of 2, and we want the area that's outside the function, but inside the circle. So this little spot right here. So my strategy on this, I'm going to find the area of the circle from this spot to this spot, and then I'm just going to subtract the polar area of the r of theta function from really the same spots here. So I'm taking all these radius strips and essentially just subtracting the inner function from the circle. Well, in order to do that, I need to figure out what this point of intersection is. So I need to go ahead and solve for this r function, r of theta equals 0. And for that, I will need the grapher. So I am back in my y equals now. I've got my r of theta graph selected. I want to deselect my r prime because I'm not really interested in that for this part of the problem. And I need to actually also graph just the line y equals 2 so I can see where these two things intersect. For my window, I'm going to go from 0 to pi over 2 because that's the first quadrant. So pi over 2. And then let me zoom 0 this thing so I can at least see those two functions at the same time and figure out where that intersection point is. Kind of hard to find the intersection point if you can't see it and, to know if it's even the correct intersection point. So this spot right here, that's where they're crossing. That corresponds with this spot up here. As the angles increase, we eventually get to that spot. So now let me do second trace, option 5 for intersect. And then let me just do enter, enter, enter. That gives us this first intersection, about 0.9425. I'm going to store that, so there it is, drawn out here so we can see it. I'm going to store that as Q on my calculator because I'm going to be using it again. So let me quit out of there, and let me store that. It doesn't really matter what letter. I prefer Q for angles, but whatever. So there it is. Okay, so what are we going to do with this? Well, we need to figure out the area of the circle, first off, from Q to pi over 2. So I need the integral from Q to pi over 2, and we've labeled Q, so now we know what it is. And we have the circle, so that's going to be 1/2 times, that's just going to be 2 squared d theta. You don't really want to use geometry in this situation because it's not really clear what proportion of a circle this is. So we're going to stick to integrals on this one. Now we have to subtract the area of r of theta, this r of theta here, from Q to pi over 2. So let me do minus Q to pi over 2, 1/2 r of theta squared d theta. And if I really wanted to on the calculator, I guess that I could move this into one integral and say 1/2 integral from Q to pi over 2 of 2 squared minus r squared, and that would also work. In fact, let me do it that way on the calculator. So here's what I did on my calculator. I had 1/2 integral Q to pi over 2, and then just the non-1/2 things inside being subtracted because we have the same limits of integration, so we're allowed to do this with our integral rules. I stored r of theta as y1. We're squaring that. Here we go. That comes out to about 0.456. For this problem, we want to find the value of theta from 0 to pi over 2, where this r of theta function has the greatest distance from the origin, and then justify our answer. So basically trying to maximize this function. But one thing we have to be careful about is that distance from the origin could also be negative distance. So we can't just take positive distance into account. We have to also figure out, if there's a negative r value that's further away than the positive r values and mess with that. So I'm going to get this started by taking the derivative of this thing, which they defined up here as r prime of theta, and finding critical values for that. So let me do r prime of theta equals 0. And I've already entered this in my calculator, so I can go ahead and solve that now. So back on my calculator, I'm in my y equals. I'm going to deselect r of theta, which I used on the last problem. I'm going to select this is r prime of theta in y2. I'm going to deselect y3 because I don't need that anymore. And now I've already got my window set from 0 to pi over 2, so let me zoom fit this again. And let's see what this thing looks like. So we're crossing one time over there, and it looks like we've got another critical value right here. So we need to find these two spots, and we're going to use those in our candidates test along with the endpoints of 0 and pi over 2. We'll plug all of them into the r function and see which gives us the most positive or negative, the furthest absolute value away from the origin. So let me find this spot first, and here's the graph that I just did. So we've got, let's see, second trace, and these are zeros we're finding. So I need a little bit to the left. Where's my spider? There he is. All right, so a little bit to the left, enter. A little bit to the right, enter. Enter again. So this is about 0.3701, and I'll call that A from here ever after. And I also need to store that on my calculator. So exit out of there and stow alpha A. Now I can use it again whenever I need to. Now let me do second trace again, go back to my graph, option 2 for zeros again. And let me arrow over to that other x-intercept. My spider moves very slowly, but that's okay. We're not judging. Move a little bit further, press enter again, enter one more time. And this is about 1.2377. And I'll call that B because I'm lacking creativity at this part in the problem. So let me now, again, go back, quit out of my graphing mode, and store that as alpha B so I don't have to rewrite it. Now I'm going to test out, again, A, B, and my endpoints in the R function. So you really shouldn't need to plug them into the calculator to find R of 0. That should just be 3 right here. We can see it. But just to be on the safe side, and you could also plug it in just directly algebraically, but just to get something in my input that I can keep using, I'm going to do alpha trace y1. That's where I stored r of theta. And let me plug in 0 just to see what happens. So that comes out to 3, as we expected. At the angle 0, you're 3 away from the origin. Now let me try A and B and then the other endpoint. So let me just yank my input from before. And now instead of 0, I'm doing alpha A, giving me about 3.928. So that's the winner so far. Let me do B now. Oops. There we go. That was a beautiful picture of my Castle desktop. But that's not really what we're showing here. We're showing value at B, which is about 1.355. That is not the winner. Now we go to pi over 2, which we can clearly see is 2 if we plug that in. But in case you don't believe me, let's go back here just because we can. And we'll do pi over 2. I'm not even going to bother with fancy fraction here. Yep, it's a value of 2. So the biggest one out of all of these happened at time, or actually the angle A. And what did they actually want here? They wanted us to find the value of theta in the interval that corresponds to the greatest distance. They don't want to know the greatest distance. They just want the angle. So we say our greatest distance then happens at theta equals A. For this calculator-based free response problem, we have the graphs of r equals 2 and 3 plus 2 cosine of theta shown in this figure. They tell us that they intersect at, let's see, this would be 2 pi over 3 up here and 4 pi over 3 down here. Well, that was nice of them. And r is that region that's enclosed by, that's inside both of them. We want to find the area of r. So to make my life a little bit easier in terms of the setup, I guess I don't need to, but I'm going to call this r equals 2 here. I'm going to call that r sub a of theta. And now this other one I'll call r sub b of theta. It just makes it easier for me to organize my thoughts with 2 different functions that actually have names that I can refer to. And one other thing I'm going to do here, and just kind of thinking ahead, if I want to find this area, my strategy is I'm going to, from this spot right here, all the way, let's see here, counterclockwise to this spot, I'm just going to be finding radius strips from my circle, my RA function. But once we get to this spot and then down to here, we need to be using our other function, this r sub b. So in order to go from here to here on my circle, I can't express this as 4 pi over 3. So this is a little tricky. If I go from 4 pi over 3 to 2 pi over 3, my calculator is actually going to treat that as a negative value. It thinks of it as like a backwards integral. So to go forward in angles, I have to call this angle down here, well, I need a negative version of this. So basically 4 pi over 3 minus 2 pi, which I can treat as, this will be negative 2 pi over 3 down here. Okay, so with that in mind, I'm going to take the integral from negative 2 pi over 3 all the way to positive 2 pi over 3, and I'm going to be taking that for my RA of theta, my circle basically. So we're doing 1/2 of that squared because we do 1/2 r squared d theta in general. So that gives me the area from here to here. To get the rest of the area from this spot to this spot down here, now I'm going to do the integral from 2 pi over 3 to, now I can use 4 pi over 3 because we're going forward in angles here. And then that's going to be my other one here, so 1/2 rb theta squared d theta. And now it's up to the calculator. So here I am on my calculator. Before I do anything else, I'm actually going to enter both of these r's here in my y equals. And I made the decision to use y equals instead of the r equals from polar mode because I don't really need to graph this, and that's really all polar mode is useful for, graphing and maybe tracing. But there's no point in tracing this because I've already figured out my limits of integration. And I might need to use these functions for something else. Really anything else, I'm going to need them in y equals mode. So quitting out of that then, let me get my integrals now. So I have math 9, integral from, we said, negative 2 pi over 3 to positive 2 pi over 3. And this is going to be, let's see, I have this stored in y1. R sub b I've got stored in y2. Let me just enter the rest of this off camera. So there's the rest of my first integral. Let me do the second one now. There is integral number 2 that we're adding now, and press enter on all this. Grand total of about 10.370. For this part of the problem, we have a particle with a non-zero velocity going along this polar curve here, this cardioid. And let's see, at theta equals 0, time is 0. It moves along the curve so that the rate of change on the curve with time and the angular rate of change are the same thing. And we want the value of dr over dt at theta equals pi over 3. Okay, so basically we have to plug pi over 3 into dr over dt. But we saw that dr over dt and dr over d theta are really the same thing. And the r that I'm talking about, I spelled it out here in my notation, is specifically r sub b, which is what I labeled this thing as. I don't know that I really needed to go to that level of specification here, but hey, better to be safe than sorry. So we already have this defined. So we were just taking the derivative of this thing with respect to theta at a specific value of theta. We're allowed to do that on the calculator without showing any other work other than what we're about to do on the calculator. So let me just go ahead and do that. So here's what that looks like on my calculator. I've got the derivative, so math 8, and I stored this r sub b in y2, doing the derivative at a value of pi over 3, grand total of about negative 1.732. So that's this right here. Now this doesn't answer the whole problem. This is this part of the problem, which we get a point for doing. But now interpret your answer in terms of the motion of the particle. Well, we have to figure out what this dr over dt really represents. This is the rate at which r is changing with respect to time. R is the distance from the origin on a polar curve. So at time pi over 3, we basically have a negative rate of change. Does that mean that we are getting less distance away from the curve or from the origin? Are we getting closer to the origin? You would think so with a negative rate of change, but you always have to check to see if the r value itself is positive or negative here. If the r value is already negative and we have a negative rate of change, well, that means you're just going backwards farther away from the origin. So let's check out the r value now. So we note that this value right here is negative because we're going to have to compare the signs of r prime and r. But let's actually take the r value now at pi over 3. So here's what I'm about to do on my calculator, r sub b of pi over 3. To do that, I'm just going to do y2 because that's where I stored my second r there of pi over 3. Comes out to, well, exactly 4. Okay, and that's a positive number. So since I have a positive radius with a negative dr over dt or dr over d theta, since these signs do not agree, that means that I'm somewhere out here and I'm moving closer then to the origin. So we would say at time pi over 3, the particle is moving toward the origin. For this last problem part, for the particle described in part B, they're telling us dy over dt and dy over d theta are the same thing. They want to know dy over dt at theta equals pi over 3, and then interpret that in terms of our motion for our particle. So first, let's find dy over dt at theta equals pi over 3. Now, we've seen that this is going to be equivalent to dy over d theta, so I need to express this parametrically now. In general, I can say that the y value is going to be r times the sine of theta. So specifically here, I can say I'm going to call this y sub b because we're talking about the y value on this second polar curve, not the circle, the cardioid. So this is going to be equal to r sub b of theta, which we've already defined. It's this thing right here, times the sine of theta. So I basically need to find the derivative of this thing at pi over 3. Now to make this legit and spell out what I'm really doing, I'm going to say dy sub b over dt, which is the thing that they're looking for here. This is what they wanted us to find specifically at pi over 3. This is going to be equivalent to the derivative of y with respect to theta at pi over 3. And now that I've spelled out that I'm about to take the derivative of this thing, I can just go ahead and do that at pi over 3 on the calculator. To make this a little bit easier to handle, I'm going to define a third function in my y equals for this y function here. So it's just the y2 function, which is where I stored that r sub b, times the sine of theta. And I could probably do without this little multiplier here, but I just really want to make sure that I'm doing what I think I'm doing. So let me quit out there now, and let me do math 8 to take the derivative, dx, and we'll do alpha trace y3 now. So we're taking the derivative of this thing, and we're still going at pi over 3. So pi divided by 3, enter, gives us about 0.50000. So we'll just go with 0.5. It's probably what it is if you actually take derivatives and all that and plug it in. All right, so that's great. That's part of the problem. We found the value, but now we need to interpret this in terms of the motion of the particle. Now this is talking about the rate of change of the particle in terms of up versus down. So when we're talking about the motion and going up, down, we can basically say, am I moving further away from the x-axis or toward the x-axis? And to make that kind of statement, we need to figure out, where am I to begin with? So we need to figure out y of pi over 3. Am I above the x-axis or below? Because that's going to determine which way this is moving us. So so this is a positive number. Let me just note that before I move on. Now let me find y of pi over 3 and see if that's negative or positive. So there we go. Y is really, again, stored as y3. And at this point, I'm thinking maybe I should have stored pi over 3 as a letter so I didn't have to keep writing it. But there it is, about 3.464. That is also a positive number. So I'm above the x-axis somewhere, and I'm becoming more above the x-axis. I'm moving in a more positive direction. Because these signs agree, that means at time pi over 3, our particle is moving away from the x-axis.